Hi class. In this lesson we're going to look at solubility. Here's a solubility graph which shows about 8 compounds and their solubilities in water at different temperatures. So immediately you'll notice that some of the curves are a little steeper than others, and some of them reach sort of an endpoint early on in the graph. So we're just going to explore this a little bit as we go through the note. The definition of solubility is the amount of solute which will dissolve in 100 milliliters of solvent. So that's the first two entries here for your fill-in-the-blank note. It's a little different than a solution concentration, which compares solute to solution volume. In this case, it's the mass of solute for every 100 milliliters of solvent. So here we can plot this as we saw on a solubility curve. Okay. Now as we go through the note, we're just going to explore different properties of solubility. First one is that, as we saw in the graph, at some point a solution will become saturated and we can no longer dissolve any more of the solute. This occurs at a specific temperature, and this point is called the saturation point. Pressure is also important as well. The pressure of the atmosphere around the solution would, for example, ambient temperature and pressure, would have a small effect on the ability of the solute to be dissolved, but primarily temperature is the main variable which affects saturation. Okay, when we look at gases actually dissolve better in cold solvents because naturally gases have a lower boiling point than room temperature, in which case the more we warm them up, the more they're going to, the particles are going to move around and they're going to leave the solvent back into the gas phase rather than the dissolved phase. So the solubility of gas is inversely related to temperature. That's why fish do well in cold water. So if you have a goldfish at home, you shouldn't have a heater because they actually need colder water because there's more dissolved oxygen. When we talk about liquids, we've seen solids in liquids, we've seen gases in liquids. When we talk about liquids mixing with each other, there's two terms that are used. When we describe limits that or liquids that mix without limit, we call this miscibility. The ability to mix without limit, in that water and alcohol or oil and gasoline are miscible. Oil and water, on the other hand, are immiscible. Means they don't mix at all and they will form separate layers. Let's just stop at this point and just have a look at a couple of examples just to touch on this point of miscibility and solubility.
Why don't oil and water mix? The hydrogen bonds between water molecules are too strong to be broken in order to produce a relatively weak interaction between water and the molecules in the oil. Thus, water excludes oil from entering the aqueous phase.
So here we're seeing a picture of the oil droplets attempting to combine with water, but because the intermolecular forces between water molecules and oil molecules are not, we could say, compatible, or rather the water-water molecule interaction is much stronger, the oil molecules are not able to get in between the water molecules and mix in together. So in order for liquids to be miscible, the relative strengths between the molecules have to be pretty close. If one liquid has very weak intermolecular forces, another one very strong, they likely will not mix.
Solid iodine is not very soluble in water. If the dense, nonpolar solvent carbon tetrachloride is added to the mixture, it forms a layer underneath the water. The nonpolar iodine is extracted from the water and readily dissolves in the carbon tetrachloride. The difference in color between the two solvents indicates that the iodine molecules interact somewhat differently with the solvents.
In the second video, the two solvents were water and carbon tetrachloride. Clearly they're not very miscible at all because we have these separate layers. However, this is also an illustration of the difference in solubility for a solute iodine, which is a solid at room temperature, and here it's partially soluble in the water. It imparts a little bit of color, but it's more soluble in the carbon tetrachloride, so it actually leaves the aqueous phase and moves into the organic solvent phase, as seen by the change in the color there. To return to our note here, just finishing up some of these points. We've seen the solubility chart before. This is useful when we're trying to predict the formation of precipitates when we combine different ionic compounds, particularly a given anion and a given cation, which are the positive and the negative ions. Not all combinations are shown, of course, but all of these compounds are ionic in their nature. When we look at the categories, they're broken down quantitatively. They have a threshold of 0.1 moles per liter, and if we have high solubility, then it's greater than or equal to 0.1 moles per liter. Now notice that's not grams per 100 milliliters, so it's a different unit for solubility, but it's not a concentration exactly. We're describing more there the amount of solvent that the amount of solute can be dissolved in. So we'd have to, again, remember that this is still solvent, a liter of solvent, and then a mole of solute. So although it has the same units as concentration, this is still a solubility value. Low solubility, of course, is less than 0.1 moles per liter. Okay, so we've used this chart enough before that's just a review. That is the solubility chart. And now let's return to our solubility curve. On your handout, you see here a smaller version of that, and there's a few questions that we just want to go through just to make sure we understand what's going on here. Temperature on the horizontal axis is increasing, and the concentration, or in this case, I would actually suggest we replace that word concentration with solubility. So solubility is being measured there, and all of them have increasing solubility with increasing temperature. That makes sense. As the temperature goes up, the energy available to break apart the crystal increases, and of course the water molecules, the solvent molecules are moving faster. They'll be able to surround the ions and separate them more easily. So that's observable. Higher temperature equals higher solubility. In looking at all the potassium containing compounds, we have potassium nitrate, potassium chloride, potassium sulfate, and potassium chlorate. So the increasing order of rate of change of solubility, so what I want you to pay attention to there is that potassium nitrate has the highest rate of change, so it responds the most to increasing temperature. Potassium sulfate, on the other hand, has a fairly flat line to it, so K2SO4 has the least increase in solubility per degree Celsius. Followed in potassium sulfate would probably be potassium chloride, and although it reaches has higher solubilities for the lower temperatures than potassium chlorate, it doesn't increase as much. So potassium chlorate is more responsive to an increase in the heat provided. Looking at the ammonium containing compounds, so we have ammonium hydrogen carbonate and ammonium chloride. What do you notice about those? Well, ammonium chloride is always more soluble than ammonium hydrogen carbonate. It exceeds it at every temperature. So we could state that at each temperature, the solubility of NH4Cl exceeds NH4HCO3. Okay, You notice we also see in the chart that the hydrogen carbonates, the ammonium hydrogen carbonate and the sodium hydrogen carbonate, seem to have a bit of an end to their curve. So what's unique about that is that the curve stops, which we can assume indicates that it reaches a maximum solubility at a fairly low temperature. So whereas the other ones, potassium nitrate, very soluble compound. Remember, nitrates are highly soluble, and we would expect them to be having the highest solubility values, but they too would reach a maximum. But ammonium carbonate and sodium hydrogen carbonate and ammonium hydrogen carbonate reach a maximum. So a maximum solubility occurs at 30 or 60 degrees Celsius. Okay, so that's the end of this video lesson. What I would like you to do, because it was a short lesson, is to go through numbers 1 to 4 on your own right now. Numbers 1 and 2 will require you to refer to the solubility curve, which is in your note. Numbers 3 and 4 are qualitative, and you should be able to reason those out by just reviewing the content related to the solubility of gases and liquids. And number 5 we can leave for working on together in class. Take care.